Okay, another installment of a BAVEV, Brother Bailey's very entertaining videos. And I think you'll find this one entertaining and informative because we are on a quest. We are trying to figure out this question. What determines diastolic blood pressure? And that's a fascinating question. We all know what this number is, right? Whenever we go, to the local pharmacy down on the corner and we sit in that machine and it tells us our blood pressure, we end up with a blood pressure reading. And let's say on average, we see this typical 120/80, right? And that's, of course, in millimeters of mercury. So we're measuring a pressure. And from our last unit on heart, we know that this value right here, the top, which is systolic, the bottom is diastolic. This top value, 120 millimeters of mercury, comes from ventricular systole. This is the pressure generated by the ventricle. But then, if you remember from that cardiac cycle, as pressure dropped because the ventricle relaxed, the overall ventricular pressure dropped to near zero, less than 5. And yet out here in the arm, as I measure on the cuff, I have a diastolic pressure of 80. Diastole in the ventricle is 5. Diastole in my arm is 80. And I want to understand what this is. Where does that pressure come from? What generates it? And how does the body regulate it? And of course, why is that pressure even necessary? Why do I need a diastolic blood pressure? Well, to begin to understand this, we want to understand first and foremost the true relationship between pressure, flow, and volume. And there's actually a very simple mathematical calculation for this. We know that pressure is simply the product of flow. This is flow. This is, of course, pressure. And R, what we really want to talk about, which is resistance. Think of resistance as friction, that which is impeding flow. Just to highlight this, we can think abstractly. Let's say I have a tube that's got the perfect diameter of a steel marble, a little steely. And I take that steel marble and I stick it in the tube and I try and push it through. Now, what might decrease the resistance and better increase flow? Well, what if I lubricated the inside of that tube? What if I had a little bit of grease and I stuck it in there and then I could stick that marble in there and push it through fairly easily? Let's reverse that. Let's think of maybe putting sandpaper or something gritty with a lot of friction on the inside and then try pushing that marble through. You can appreciate that by increasing the resistance, I've decreased the overall flow. And so in this way, we see that pressure is going to be a combination of these two things, flow and resistance. Now, mathematically, we can actually calculate the resistance of fluid through a tube. This is given by the equation R, again, where R equals resistance equals 8, this funny looking N thing, which is eta, L over pi R raised to the 4th power. Now, let's just quickly define our variables. The ones that are, let's see, we already defined N, eta. This is viscosity. You can think of it as the thickness. It's not really the thickness, but for now that's good enough. Think about it as the thickness of the fluid. There certainly is a difference in viscosity between water and that really thick buttery syrup that you poured on your pancakes. L is length. And you can appreciate that this is directly proportional to resistance simply because the longer the tube, the longer it takes me to get through it. And then lastly, R on the bottom, radius. And because it's in the denominator position, we recognize that this is going to be inversely proportional to resistance. Now, the beauty of this, let's be honest, we don't want to deal with all of these things. In the human body, guess what? Blood has a constant viscosity. 3.04 times 10 to the minus 3 Newton seconds per meter squared, and I don't care. It's a constant. 8, it's a constant. It's just 8. Length. Well, for the most part, you and I, now that we've stopped growing, we have a constant amount of blood vessels. That's not something that's dynamic. It's not something that's changing a whole lot. So that also is a constant. All of these are constants. And this allows us to really see what this equation means for us. What it means is that resistance is proportional to 1 over the radius raised to the 4th power. Everything else in that equation was a constant. But radius, that's something that we can change. Now, to highlight this, let's look at an example. We'll keep that equation right there, and let's draw a tube. This tube has length L and radius R. There's a couple of ways that I could increase resistance. Let's consider, for example, increasing the length. Increasing L. What would that do? That would, let's come back to scenario where we have this tube that's twice as long. So now my overall length is 2L, still with radius R. Based on what we see up here, what have we done? We have increased, this will lead to an increase resistance by a factor of 2, twofold. Essentially, we just doubled it. And we can see that from the equation. If I double length, I double resistance. Now, consider if we take another option and we keep the same length, but we reduce radius R. So now we've got a tube that's got half the radius, but we maintain the same overall length. Remember, because radius is raised to the 4th power and it's inversely proportional, as my radius goes down by half, my resistance, what's going to happen here? This is going to lead to an increase in resistance by 16-fold. Right? This is a huge increase in resistance simply because my radius was cut in half. So what this teaches us, and again, we mentioned earlier, the overall length of the blood vessels in our body isn't changing. The true way to increase or decrease resistance is by changing the radius, the overall diameter, the size of the blood vessels through which the blood is traveling. Now, there is one other thing that we have to think about before we start to put this together, and that is the difference between series and parallel. Let's consider running tubes in series. Okay, we're going to come back to these tubes, and let's say we have 3 tubes. We have this one. All the radiuses are going to be the same, but the lengths are going to be different. And based on what we just saw, we know that by increasing length, we're going to increase the resistance. So let's say that this has a resistance of 5. This one's doubled, so this has a resistance of 10. And this one's a little bit shorter, so let's give this one, say, a resistance of 3. Well, in series, the total resistance R total is going to just be the sum of the resistances. This is going to be R1 plus R2 plus R3. And that makes sense because we're just making this really, really long. So what do we get? We get 5 plus 10 plus 3. This gives us a total resistance for this scenario of 18. In series, the sum is always greater than any individual component. The sum is always greater than any individual component. But let's contrast that with what happens in parallel. Okay, we have those same tubes, but now instead of going through them one at a time, we split up and go through all of them at the same time. We have this one here, that was 5. We have this one here, was 10. And then we have the short one, that was 3. And we've split up and we've gone through all of them at the same time in parallel. Well, in this scenario, my total resistance, our total, is going to equal 1 over R1 plus 1 over R2 plus 1 over R3. In other words, for this scenario, that's going to be 1 over 1/5 plus 1/10 plus 1/3, which comes out to be 1.58, if I do the math right. Now, look at the difference between these. Up here in series, we added everything up, and the sum was greater than any individual components. But here at 1.58, the sum is smaller than any one of the components. And that's what happens when we run in parallel. It's always less than any one component. All right, the very last thing we have to make sure we understand before we start putting all this together is we have to understand the idea of the total cross-sectional area. So now let's look at the cross-section. We see for any given circle with radius r, well, let's just assign this. Let's say the radius equals 1, just for easy math's sake. And then let's add a couple more. Again, same radius. Now we've got 3 tubes, and this kind of helps us understand what running in parallel, how it reduces resistance so significantly. We know that the total area of a circle is going to be pi r squared. Of course, in this scenario, we said r equals 1, and so that's simply going to be pi times 1 squared, which is just pi. As I add them up, that area plus this area plus this area, the sum total is simply 3 pi for this scenario. This is the sum of cross-sectional areas. So this is what I want you to recognize now. The radius of the new cross-section, right, as I add all of these circles together, the new radius is going to equal 3 pi is going to equal pi r squared. So 3 equals r squared. So my new radius of all of these together is equivalent to the square root of 3, or about 1.73. So even though I have one initial radius of one circle, by adding multiple circles by running in parallel, you can see that the overall cross-sectional area is proportional to this radius, and we get a perceived increase in radius. And as we increase in radius, what happens? Because it's inversely proportional to resistance, then as my radius goes up, because my total cross-sectional area increases, then my resistance goes down. Now, what does that have to do with understanding blood pressure? Well, let's try and apply it to a scenario that we might see in the body where we know we're coming out of the heart, we've got this big aorta, it's bringing all this stuff, but eventually we're going to hit a bifurcation, right? We're going to have to split. And so we've got this blood vessel and we're coming along, but then we split. Now, there's a couple of different scenarios to think about. What if in this split, the overall diameter, well, let's just keep with resistance. So here's resistance R, but now this radius R, and this radius, they're all the same. Nothing has changed. Well, if we look at that, we know what's going to happen. We haven't changed radius, but we have split, so we're running in parallel. So what would we expect to happen? A huge decrease in the overall resistance. And if the resistance goes down, because it is proportional to pressure, as my resistance goes down, what happens to my pressure? My pressure drops. So this doesn't work. What do we then have to do? Well, let's take that same scenario. We hit our bifurcation, but now we make our blood vessels that are branching off, now we make them a lot smaller. Of course, if we make them too small, because remember, this is 1 over radius to the 4th power. If we make them too small, resistance skyrockets. And so having them too big or too small doesn't work. It would mess up all of the pressure systems in the body. So if I run some math based on what we're doing, I don't want to bother you with numbers anymore, but if I run some math, it seems like when we hit a bifurcation, we need about a 15% reduction in radius in order to not affect pressure.